Thank you, Misha, for the introduction. And hello, everybody. And thanks for the invitation and this privilege of giving the last talk of the year. I would love to be there with you in person, but yeah, the times are too uncertain to travel. Yeah, hope to come another time. So here that is the topic, and it is like the talk will be based on the work I've been doing this year together with Andrei Shkerin. So the original question is theoretical one, and actually it has a quite long history by now. Basically, the question is how. So imagine we have a theory where we have a false vacuum that decays, and in principle we have a formalism. We know how to describe it using, say, Coleman's instanton approach. And this is quite general situation. Well, it appears in field series, well, the unstandard model, actually perhaps in the standard model, as I will discuss further on. And it also is relevant for statistical systems. So now the question that I will address, how a presence of a black hole will affect the decay rate. And actually, how should we describe that? So this early works, by Hiscock, Arnold, and Berezin, Kuzmin, Tkachov, they first formulated this question and they formulated the question but didn't formulate the answer. So what they did, they studied various solutions in Euclidean time, similar to Coleman's approach, following like the instanton approach, and interpreting these solutions as perhaps describing the vacuum decay rate. They found that in general black holes do catalyze vacuum decay, but it has been unclear what these solutions mean. Actually, do they really correspond to the physical processes, or they are just some spurious solutions? So like a consistent formalism has not been developed, for 30 years. Well, besides this purely theoretical interest, it may also have some phenomenological implication. I mean this question, because primordial black holes may exist in our universe. There are models of inflation and some other models of our universe where primordial black holes are produced with actually any mass. I think for any mass of black holes, there will be a model. And here I summarize the constraint on these primordial black holes in the range of masses from about 10 to minus 17 solar masses to 10 to 20 solar masses. I mean, there are a lot of constraints, and the constraints are in terms of fraction of these primordial black holes as possible dark matter. We see, like in this range, essentially, the black holes cannot be dark matter. Of course, the constraints here, they have different different level of robustness. So most robust constraints are those coming from the lensing experiments, lensing observations. Then there are other dynamical constraints and so on. Yeah, I'm not going into details of this plot. Yeah, just interesting fact is that there is a window between 10 to minus 15 solar mass and 10 to minus 12 or 11, where actually primordial black holes can be all of dark matter. On the other hand, here on this side, there are very strong constraints, which come from the fact that lighter black holes will evaporate during the lifetime of the universe. And like black holes with this mass, they will be evaporating kind of now or recently, and will produce a flux of hard radiation, which we don't observe. So that gives these constraints. But if we move further to even lighter masses, those black holes would operate very early, and essentially there are almost no constraints there, as one would think naively, at least. Okay, so let me review briefly black hole evaporation. So, according to Hawking, from works of Hawking, we know that black holes emit thermal radiation with the temperature which is inversely proportional to their radius. And in turn, the radius is proportional to the mass, so the temperature is inversely proportional to the mass of black hole. So the smaller is black hole, the hotter it is, and like in the process of evaporation, it scans all the masses from original, which may be very low. Yeah, the black hole is small, is big enough, but then the temperature will increase and reach perhaps Planckian, or perhaps an order of magnitude below Planckian. After what the black hole will explode, and we don't know precisely how, but it doesn't matter very much. I mean, we just know that the temperatures, yeah, if the black hole mass stays at least an order of magnitude above Planckian, we may trust the semiclassical approximation, the semiclassical description of Hawking, and in that case, the temperature of black hole will be already very high, just an order of magnitude below Planckian. Yeah, the lifetime of black hole can be calculated using, just this energy conservation law, and it is proportional to the cubic power of the initial black hole mass. So black holes of solar mass, they live essentially forever, much longer than the age of the universe. But yeah, if we put here something like 10 to minus 17 solar masses, then we will see that such black holes will disappear before present age. And yeah, I already mentioned that black holes in the range of masses roughly between 10 to 9 grams and 10 to 17 grams, they would be evaporating quite recently. And so that gives strong constraints coming from Big Bang nucleosynthesis, spectral distortions, and so on. Whereas black holes lighter than 10 to 9 grams would evaporate before BBM. And so it looks like there will be no constraints on them, and I mean, their radiation product will just thermalize. These black holes, which evaporate very early, they have been considered in the literature, and recently they haven't even, there was a wave of interest in them. They can produce a lot of interesting things in cosmology, producing heavy dark matter, catalyzing baryon asymmetry, and so on and so on. But yeah, the question is it true that there are no constraints on this type of black holes? This statement was questioned in the works by Ruth Gregory, Jan Moss, and collaborators. They started from the following observation, that actually the Higgs vacuum in the standard model can be metastable. Well, actually, according to what we know about standard model now, I mean, about the parameters of standard model, it is metastable. So we are here, this is our electric vacuum, but then due to radiative correction, the Higgs potential goes down, it bends out, bends down, and goes to negative values at field values of the Higgs around 10 to 11, 10 to 12 GeV. So yeah, so like the system or our universe can tunnel from here to here. Of course, this is true. I mean, this potential is true only if there is no new physics, beyond above, well, somewhere in between, In principle, yeah, new physics can change its behavior and can curve the potential up and down. Actually, it can change both ways, make our vacuum more unstable or more stable, or even stabilize it completely. But yeah, but if we just stay within standard model and the currently measured parameters, that's what we have. Yeah, by the way, feel free to interrupt me at any moment if you have any questions.
Yeah. Sorry, I have a question about the plot. So you said that the potential can go up again. So, but does it have to go up again? Otherwise, there is no other vacuum. So how does it work? Like it can go actually down?
Yeah, it just can go. Yeah, it can go down indefinitely. There will be no true vacuum. So yeah, the system will basically go into runaway. Yeah, so right. Like the tunneling will result into a runaway solution. Yeah.
Yeah, we'll have
I mean, for the standard model Higgs, this vacuum, if any, it is somewhere beyond Planckian values of the field. So kind of quite, how to say, it's equivalent to saying that there is no true vacuum at all, because it's beyond Planckian where we don't trust this description anyway. Yeah, so for all practical purposes, just the potential is just unbound.
Okay, thank you.
Yes, I have a question here.
Yeah.
About primordial black holes. I don't know if you're aware, Grisha Vilkovitsky claims to have calculated the back reaction of the evaporating holes on the metric, and he says that they don't evaporate entirely. They evaporate about half their mass before the back reaction stops the Hawking radiation. His papers are much too hard for me to understand, but I'm wondering if there's any consensus on that.
I stick to more like traditional viewpoint that semiclassical description works as long as black holes are heavy enough, so they would evaporate a la Hawking. Of course, this evaporation description or this thermal radiation is an approximation. So perhaps if we look more closely at the radiation, it won't be exactly thermal. It will have certain correlations, so that the unitarity of the process of black hole formation evaporation is preserved. But from just energetic viewpoint, I think there is emission, of radiation, and black holes lose their mass according to that formula.
So is there any consensus? Do you know of any consensus about whether the back reaction at some point stops the evaporation?
Well, I don't think there is a uniform consensus, but I think the prevailing viewpoint that evaporation does not stop at least before the black hole reach Planckian masses.
Okay.
In your formalism, like you are not considering extremal black holes, right? Like charged black holes.
No, here I'm studying just uncharged black holes, Schwarzschild black holes, to be more precise, non-rotating.
Okay, thanks.
Okay, so the probability of tunneling in like an empty space and from the vacuum is calculated using this Coleman instanton approach, and it is exponentially suppressed with this exponential suppression given basically by this formula where alpha is the Higgs coupling constant. Okay, some coupling constant. Yeah, okay, yeah, it's Higgs coupling constant, but it doesn't matter that much which coupling constant. What matters that this coupling constant is small, so that this suppression is large, and the decay time in empty space is something like 10 to 400 years, which is again infinity for all practical purposes. However, if we put this system in thermal bath, then the probability of decay grows. That's the usual story that phase transition, they prefer to happen at higher temperatures. And at high enough temperature, actually the dominating process is not tunneling, but are jumps over the barrier. And the probability of these jumps is given by, it's again exponentially suppressed, but now it's suppressed by the ratio of the energy of the barrier to the temperature. And if temperature is large, is comparable to the height of the barrier, then this process would become unsuppressed. Here that would happen at if I just take this potential, it would happen at temperature around 10 to 14 GeV. It's also true that in standard model, the situation is more tricky because this falling around energy here, the height of the barrier actually gets large thermal corrections due to large number of species in the standard model. So in principle, this correction may or may not stabilize completely the vacuum with respect to thermal decay. And that again depends on the parameters of the standard model, and is quite sensitive to some couplings that we even have not measured with enough precision so far. But I think the qualitative picture to take from here is that at high temperatures we in general expect the vacuum decay to be less suppressed than at zero temperature. So now let's combine this metastability of standard model vacuum with the fact that black holes evaporate. Let's put black hole inside. And black holes, as I said, they scan all temperatures from perhaps low to Planckian or about Planckian. At the final point, they perhaps explode. But anyway, what is important that they scan all these temperatures, and in particular, they will reach the temperature which corresponds to the height of the barrier in the Higgs potential. And if we take this picture and calculate the suppression, we actually find that it decreases with the black hole mass and reaches and becomes like of order 1 when the black hole mass is about 100 Planck masses. So black hole is still semiclassical at this point, but there is already no suppression for the Higgs decay, and that's what was claimed in the literature. And this actually gives a tremendous, well, it has tremendous consequences for these primordial black holes, because it means that even a single primordial black hole in our universe would trigger vacuum decay without any suppression, essentially with probability order 1, and would completely destroy our vacuum. In other words, there can be not a single evaporating black hole in our past. So either.
Can I ask a question? Can I ask a question?
Yes, of course.
If you go back to your plot, the temperature increasing is getting faster and faster. Is there any way in which you have this high temperature for sufficiently small amount of time, or in a sufficiently small region, that in the end it doesn't lead to a decay or something, or that you can never make such a thing happen?
Well, about small region, I will say, about like in space. Actually, I will come to that. So as for time, you can ask if, say, some quasi-static approximation, which is presumably used in this calculation, if it's valid for, for these small black holes. And the question is, the answer is that it is valid as long as the characteristic size of the bubble is smaller than the black hole evaporation time. So, and this is satisfied. Yeah, like temporal characteristics are all right. For special homogeneity, actually, that's where I'm coming.
Okay, thank you.
So this calculation, which was done in the literature, it has a caveat. Actually, this calculation follows quite closely the instanton approach and looks for periodic instantons in Euclidean time, which is all right for a situation when this black hole is in thermal equilibrium with an environment. So so basically we have a black hole immersed, radiating with Hawking temperature, but also being in the bath with the same Hawking temperature. And in the black hole kind of physics, this state goes under the name of Hartle-Hawking vacuum. So black hole in equilibrium with the environment. And that's not what is realistic. The realistic picture is when black hole evaporates, that's all right, emits thermal radiation, but there is no radiation outside. So a realistic black hole is not in thermal equilibrium. This is described, this quantum states, here's the name of under vacuum. It's a different quantum state. And on physical grounds, we expect it to be actually less prone to decay. Because now, say, we don't have any particle that, that this particle can collide with. Yes, in thermal bath, this radiation can collide with another quantum coming from the bath and perhaps create a transition. But here, we don't have anything like this. So for a realistic black hole, we actually don't expect that exponential suppression completely disappears. We rather expect some curve like this. So as the mass decreases, the exponential suppression perhaps goes to a constant or even start increasing at small mass. But so far, that's what. But this picture is just what we expect. So that was pointed out perhaps first in this work, like clearly pointed out. And they gave a few qualitative arguments why it should be the case. So one argument is that when the black hole is very small, so very small, very hot, okay, in the limit of very hot black hole, but also very small, its size is much smaller than the size of the critical bubble that we expect to produce. Yeah, because the size of the critical bubble is given by roughly by the mass of the scalar field that is tunneling. In that case, even if I have a large number of soft quanta in the vicinity of the black hole, this number like of soft quanta that are supposed to produce this bubble, it is given by the ratio of temperature to the frequency of this quanta, and it is very large in the vicinity of the black hole. Still, if I go away from the black hole to the distance of order of the size of the bubble, this number, this density of quanta will dilute just due to geometric, geometric factor. Yeah, it will dilute as the area of the corresponding spherical shell. And yeah, if I put all things together, I actually get that the density or occupation number of soft quanta at the distance comparable to the size of the bubble is actually much smaller than unity. So black hole is not able to produce a large coherent state with the size, with the needed size. So I expect that the critical bubble, the production of the critical bubble will be suppressed, exponentially suppressed. So Matthias, does it answer your question?
Yes, thank you.
So they also gave a second argument, also related to the same fact that the bubble is much larger than a black hole, that this number of thought quanta, even in the vicinity of the black hole, is actually not large. It's suppressed due to greybody factors of black hole, because black hole is separated from outside by a potential barrier, centrifugal potential barrier. And due to that, the probability to emit a single soft quantum is suppressed by the product of the frequency of this quantum times the radius of the black hole squared. So again, we get suppression of probability to emit a single quantum. And if I want to make a coherent state made of many quanta like that, I have to multiply this probability, by the number of, to multiply it, to take it to the power of the number of quanta I want to produce. So here it will give me like a small ratio to the power, which is inversely proportional to the coupling constant. Yeah, because the number of soft quanta which make the critical bubble is of order inverse coupling constant. And this probability now to make the critical bubble is exponentially suppressed, again, according to this picture. But as you see, all these arguments are qualitative, and the question is how to make them more quantitative. Yeah, how to compute actually this minimal suppression. This minimal suppression, because we also it's not just again of purely academic interest, but if we really want to analyze the phenomenology of these models with primordial black holes, we actually need to know this number, because the universe is large. Yeah, and the universe, I will have exponentially large black holes in the typical mechanism. So I have like two exponential factors, exponential large number of black holes, like two competing factors. Yeah, one is large number of black holes, another one is exponentially small decay rate. And the question which wins. Yeah, for that I need to have to be able to compute this minimal suppression. And that's where I'm going now. Right. So beyond, before I go there, actually, beside this phenomenological motivation, I think, there is also other motivation, maybe more like speculative, but and vaguer. But I think it's still there. At least I believe it's interesting to study this process for a few more reasons. So one is that this is a non-perturbative and non-local process, as any tunneling phenomenon, and it will teach us something about QFT and curve geometry, which is nice. We don't know what it will teach us, but it will teach something. Second, that being semi-classical, in principle, we can quite straightforwardly include back reaction of the tunneling field on geometry, and in this way, including effects of semi-classical quantum gravity. And again, we can perhaps learn something about semi-classical quantum gravity in this way. And finally, like it was already shown in the works of Gregory et al., that black hole mass is likely to change in this process. And actually, just by energetic arguments, it should change. Yeah, once I include this back reaction. And in particular, it can increase, but it also can decrease, perhaps. And then we may ask questions: where does the entropy of black hole go when this decay happens, and see if it can teach us something about entropy of black hole. Good. So then we come to the idea of setting up the calculation, and we encounter certain issues, certain puzzles. which are perhaps technical, but also when you think about a bit about them, maybe they are not so technical. They look, yes, somewhat somewhere in between technical and conceptual. Well, so say one question. The first question is actually, where does this bounce lead? Yeah, with instantons in like empty space or in thermal bath, we know that we should just go to Euclidean space, and that's what we will get. Sorry, not Euclidean space, but Euclidean time, and basically look for solutions there. But now the system is out of equilibrium, so we cannot go to Euclidean time. But then what should we do? And it's not clear. I mean, yeah, where does the relevance of the classical solution live? Does it exist at all? The second one is, okay, you say, okay, to formulate this question more precisely, I need to define what is the initial quantum state from which I tunnel. But then in the context of black holes, you encounter another problem, because in black holes, you can choose different quantization surfaces. And like a complete quantization surface would encompass both the outside of black hole, but also inside, and even the other asymptotic region on the other side of the black hole in the fully extended Tortoise coordinates. But that doesn't seem to make much sense, because these regions, we know, they are just mathematical artifacts. They don't exist in realistic black holes that form from collapse. So, okay, then you can say maybe the quantization surface should be like this. So it should be, it includes the portion outside and the portion inside black hole. But then it would imply that the final answer would decay on what happens inside the black hole. But that's again strange. Yeah, if we are outside observer and we are interested and we are just looking at this black hole from outside, it's not clear why anything should depend on the details, how this, what happens inside the black hole, or what we throw inside, or what dynamics is in there. So it would be nice to formulate somehow the question, on the surface which is entirely outside, but then there is no, like, the quantum state. The full quantum state is not defined just outside. Yeah, at least it's not a pure quantum state. Okay, I will come back to that on the next slide. And imagining that we even managed to kind of find the relevant quantization surface, the question is, how do we distinguish different vecua on this surface? Yeah, what does distinguish different vecua? How different solutions that correspond to different vecua. In particular, I want to impose the Unruh vacuum. So what does it mean? And to address these questions, like first simplification that we will do is to assume that the black hole metric is static. So basically we don't, we neglect the back reaction of the tunneling degree of freedom on the metric. And that is okay, provided certain inequality between the parameters. Okay, let me see how I'm doing on time. Oh, okay, good. So, right. So we have to formulate this question, starting from first principles. And here we go back to the basics, and we remember how Coleman derived his, his formula. Also other people before and after Coleman. And what we have to do, we have to basically consider the path integral that over all trajectories that connect the initial state, which is somewhere near the false vacuum, to the final state, which is somewhere near the true vacuum. And we integrate over all trajectories that connect the two. Then the decay probability is given by the square of the amplitude, summed over all final states in the basin of attraction of the true vacuum. And writing down the full path integral, we get something like this. So here we integrate over all trajectories in between over initial conditions, actually twice, because like the initial state enters in this formula twice. Then we have we have overlap or wave function of the initial state in the coordinate representation, and the action of the action of the trajectory which connects the initial and final states. Yeah, and we sum and we integrate over all trajectories. Where do they live? Okay, they live actually on the contour, which is like doubled like this between the initial time and final time, and then going back to the initial time, because we have the structure of the product of two amplitudes. And this contour, it must be familiar to those who are familiar with the in formalism. Basically, that's the one which is used in the in formalism to calculate averages in arbitrary initial quantum state. So here, if you want, we are calculating the average of the projector on the true vacuum. Good. So that's already good. Yeah, and given this understanding, we now also know how to generalize this formula right away for mixed states. Yeah, in the previous slide I had the pure initial state, but now I can also take a mixed initial state, and again I just calculate the average of the projection on the true vacuum over the initial state given by some density matrix rho. So that in the initial the form factor related to the initial state will have this form. It will be essentially the matrix element of the density on the density matrix, between this phi I and phi I prime, over which I integrate. Okay, yeah, let me see. Okay, yeah, what is important is actually what this form factor gives. So this form factor, its role is to set the boundary conditions for this path integral. Yeah, I must say here that of course I expect to take this path integral using the saddle point approximation. Yeah, because I'm working the semiclassical approximation. So I will take a saddle point which will be solution of classical equations of motion along this contour. Though the solution need not be real. Yeah, it may be complex, and actually it will be complex in general. And the boundary condition for this solution will be set up by this form factor here. And if I look closer at what these conditions are, they're actually the same as for the Green's function, for the time-ordered Green function on this contour. Because essentially the Green's function is given by the same path integral. The Green's function in the informalism. And given that I know how to do things for mixed states, then in the case of black hole, I can really restrict to the outside region. So I can perform the whole condensation and define my vacuum states on the portion of the surface which is outside the black hole. Different vacuum states will be just different mixed states on this surface. Yeah, let me skip the slides about the boundary conditions unless there are questions here. Yeah, because it's a bit too technical. And let me just summarize. So the summary is that we need to solve classical field equations on the inner contour that goes around along the real axis. Okay, it actually may be deformed in the complex plane. This deformation may be actually required to find a non-trivial classical solution. And the boundary conditions are the same as for the causal Green's function on the same contour. Then the suppression, exponential suppression, will be given by the classical action of this bound solution on the contour. You may wonder how it's related to what we know, from textbooks, how it's related to the Euclidean time picture. And it turns out that in the cases that we're familiar with, this procedure is equivalent to the standard one. For example, if you consider vacuum bounds, like decay from the vacuum state, then the boundary conditions which I get on, from my formalism are equivalent to Feynman boundary conditions. As I say, that they're the same as conditions on the Green's function, and in the case of vacuum, these are just Feynman. This is just Feynman Green function. Given these Feynman boundary conditions, they basically say that the field is analytic in the upper half plane, and separately analytic in the lower half plane. Yeah, and it has a branch cut somewhere here. So what I can do, I can deform the contour to Euclidean axis. And on this Euclidean axis, I just get the standard, the standard picture of Euclidean instantons or Euclidean bounds. Similarly, for thermal states, the thermal boundary conditions on the sides of the contour are such that they enforce the field to be periodic in Euclidean time. And then I can take this contour and deform it into into this. I don't know how to call it, this P-shaped or pie-shaped contour with a portion on the Euclidean time where just standard periodic instanton lives, and two parts which go along the real axis. And in principle, the solution is non-trivial here, and its action gets a non-trivial contribution from these parts. But because of periodicity of the field in the Euclidean time, these contributions cancel. So eventually, I end up with vacuum decay rate given just by the Euclidean periodic instanton. Are there any questions? Okay, I don't see. Okay, so here we are coming basically to the statement that good, we now have a general kind of boundary value problem, but it's a hard problem. So it can be solved numerically because the task is just to find the classical solutions, but it's hard. And here is a good time to go to to make further simplifications. And I cannot withhold citing Freeman-Dyson here that if we really face a very hard problem, let's simplify to go to one dimensions, and hoping that things will become much clearer, much simpler, maybe not clearer. And indeed, that's what we try to do. We devised the toy model just to make sure that this formalism just to see how this formalism can be applied to in some realistic context, or to some setup. In 1+1 dimension, we have an analog of Schwarzschild black hole, which are called Dilating black holes. So these are solutions of two-dimensional gravity coupled to a scalar Dilating field. The metric looks like this, and Dilating field is just linear in radial coordinates. This metric function has a zero at certain value of the coordinate, which is analogous to the black hole horizon in 4 dimensions. And the temperature of black hole is given by lambda over 2 pi, where lambda is the parameter of Dilating gravity. So here there is a difference between 2 dimensions and 4 dimensions. 4 dimensions, the black hole temperature depends on the black hole mass, whereas in 2 dimensions it does not. It's just fixed by the parameters of the model. Okay, then we can go to Tortoise coordinates. This part of the analysis is completely similar to 4 dimensions. And in the Tortoise coordinates, okay, let me go back. So in the Tortoise coordinates, the outside of the black hole corresponds to the full axis of the coordinate x, from -infinity to infinity. That's where we are going to define our vacuum states. For the tunneling field, we'll choose the following model. So it's here's the action. So it has just the usual kinetic term plus a potential. So it's a very simple system. And for the potential, we choose, it's made of 2 parts. So it's a mass, there's some mass and Liouville potential. So why Liouville? Because Liouville potential admits general solutions, like a general. It gives a solvable model, at least at the classical level. So we have a general solution, and we just deform this Liouville potential by the mass to ensure that we have a well-defined false vacuum. Then the full potential looks like this. So actually, like qualitatively, it's quite similar to what we have in standard model. There's a false vacuum, then a potential barrier, and then a cleave and the potential goes to minus infinity. The coupling constant that controls semiclassical approximation here is alpha, which is we just took out in front of the whole action, and it is assumed to be small. And another assumption, okay, which is instrumental to really find analytic solutions, is to assume that there is some hierarchy between the parameters of the Liouville potential and the mass. But yeah, maybe there are technical things. So what we have to do is to, so as I said, the Liouville model admits general solution. So now we are looking for the bounds by kind of asymptotically expanding the equations and match. So we find solutions in the core of the bounds where we believe that where we neglect the mass. And there, the full solution is just given by the Liouville theory. And separately, we solve the equation outside, at the large distance from the core, where the equations are essentially linear. So we can find the Green's function more or less explicitly. And then we just match the two. To find the solution, outside the core, we need to find the Green function, and for that, it is important to expand the field in the eigenmodes. That's where this effective potential appears. So, like eigenmodes of the field in this background, they are given by the solutions of this Schrödinger type equation with an effective potential that changes from 0 at minus infinity in these coordinates, which means like close to the horizon, to the mass, like asymptotically to the mass at the asymptotically flat region. So there are different types of modes. There are modes which are incoming, toward the black hole. They are depicted here in green, and they can have energy only above m square, or frequency above m square. Well, above m, sorry. And there are also modes that, like outgoing modes, which also to propagate to infinity must have a frequency above m. But then there are also modes which are localized in the black hole, and they also play an important role in the calculation of the Green's function. But yeah, I think what is important to say here is that the Green's function is dominated by the modes with frequency of order mass, which we assume to be much smaller than the black hole temperature. That's also what allows explicit calculation of the Green's function. And here are results for the tunneling rate. Okay, let me explain this rather busy plot. So the green curve here is just tunneling rate from thermal bath in empty space. So this green thing is without a black hole. And of course, because the system is analytically tractable, we could calculate it analytically. And as expected, it decreases with temperature, and eventually goes to 0 at very high temperatures. It decreases 1 over lambda. I remind that lambda is temperature. The blue curve is the suppression of decay rate of the Hartle-Hawking state at the same temperature. So now this is with black hole, and we see that actually this decay rate is even less suppressed, so it's more probable than just in thermal bath. So black hole has a double catalyzing effect, like of the temperature, but also some geometric effect. So basically, like the bubble in curved geometry happens to have smaller action. Okay, and again, this of course decreases to 0, but that's expected because as I remind you that Hartle-Hawking vacuum is a state of black hole in thermal equilibrium with surrounding bath. Most interesting curve is the red one, and that's the suppression of decay from under vacuum. So we see that it is more suppressed than the one from Hartle-Hawking, as expected from my qualitative arguments. But nevertheless, it also goes to 0 at very high temperatures. So at this point, one may be puzzled. Did we? I mean, what does it mean? Is it result an artifact of 2 dimensions, or it will be also applicable to 4 dimensions? And the claim here is that it's actually, I mean, this particular result is an artifact of 2 dimensions because we forgot something in this model, in this toy model, which is kind of natural for 2 dimensions. It lacks one important feature, which we have in 4D. And this is the existence of the potential barrier, or the centrifugal barrier, which separates the near horizon region from the asymptotic infinity. So in my case, I just have a monotonic effective potential that doesn't have any barrier here. In 4D, we have a centrifugal barrier, which is inversely proportional to the square of the black hole radius. So it is proportional to the black hole temperature squared. So the smaller the black hole, the higher the barrier. And the question is, can we model this barrier in staying within 2-dimensional solvable model? Remarkably, it turns out that yes, we can do that. In fact, it turned out to be quite simple. We just need to introduce direct coupling of our scalar tunneling degree of freedom to the dilaton, with a certain coupling which is in our hands. And yeah, that will produce the potential barrier. Moreover, it's a kind of situation is even better than in the case of 4D, because now we have this coupling, this overall coefficient here under our control. We can choose it to be large, small, or whatever we want. And if this coefficient is much smaller than 1, then the model is still analytically solvable. And in this case, that's the picture we get. So the decay of the Hartle-Hodgkin vacuum is still like this, the corresponding exponential suppression still goes to 0 as before. Well, again, that's something to be expected. But what is important, that the suppression of the under vacuum does not go to 0 anymore. It goes to a constant at very high temperatures. Yeah, and that's a qualitative change, from the simple model without barrier. So the moral from here is that actually the gray body factors are really important, as I discussed in the beginning. They're not just quantitatively; they're actually qualitatively important for the behavior of the decay rate. Good. So actually, I'm coming to my summary already. So first of all, we developed a formalism to calculate the decay rate of different states in the black hole background. And in fact, this formalism is more general, so it's applicable to any non-equilibrium state in general. Yeah, though like the specific applications may be complicated. But in these toy models that we studied, we were able actually to calculate the decay rate explicitly analytically. And what we saw that the like first qualitative and quantitative statement that under vacuum decay is more suppressed than Hartle-Hodgkin, as could be expected on general grounds. But now we have a method to prove this unambiguously. Moreover, like the second conclusion, that gray body factors are important, and they qualitatively affect the behavior of the semiclassical rate. Well, yeah, depending on the height of this of the potential barrier, and once taken into account, they lead to exponential suppression of under vacuum decay at any temperature. Yeah, interestingly, that right. So under vacuum decay is suppressed, exponentially suppressed at all temperatures, but it is still catalyzed. Black holes still catalyze the decay, so that the decay rate is larger than in empty space. And given these results, it's like natural next step, and actually very interesting one, is to apply this method to a realistic black hole in 4 dimensions. There can be additional sources of suppression, but I think it's interesting find to what extent they are effective. And as I said, yeah, I think it's a matter of calculation to find the optimal decay rate and optimal size of black hole when it catalyzes the vacuum decay most strongly. This can be applied not just to an isolated black hole, but to more general situations when we have a black hole immersed in thermal plasma with temperature which differs from temperature of black hole. For example, we can have a large enough black hole whose temperature is much smaller than the temperature of thermal plasma. Still, it can have some geometric effect on the on the tunneling bubble, on the critical bubble. And yeah, if we do it very naively, we actually can find that the energy of the critical bubble due to redshift in the black hole metric can be made very small. So the question is, does this catalyze vacuum decay or not? Finally, yeah, the interesting challenge is to include the back reaction on the metric and see how like semiclassical gravity effects affect the whole picture. So thank you here for the attention, and yeah, I'm happy to take your questions.
Yeah, so I'm just gonna like step ahead many steps, and let's say that there are very strong observational and theoretical constraints, arbitrarily strong constraints on the primordial black holes. And what have we learned? What kinds of classes of models have we ruled out? Like, are there interesting models that people are very attached to now that predict formation of primordial black holes, which would be kind of ruled out by such constraints?
Well, there are classes of models that, now, first of all, let me say that kind of producing these primordial black holes, yeah, it's not something generic. But there are classes of models of inflation. For example, when some part of the inflation potential is very shallow, or something like hybrid inflation, where there can be a period of a period of very yeah, there can be a period where the potential flattens out, and that can lead to enhancement of cosmological perturbations, and which, yeah, if their amplitude is becomes closer to 1, they can lead to production of black holes. Okay, then, so there are these classes of models. Second, people have been studying some other models where basically not addressing the production mechanism, but just analyzing what kind of effects these primordial black holes can have. And yeah, they can source, well, essentially there are models which claim to solve all problems of cosmology at once, just using these primordial black holes, like reducing dark matter, generating baryon asymmetry, and whatnot. So I believe there are some people who may be attached to these models. Yeah, if you ask myself, I don't have any like super favorite model of this class, though some of them look interesting. And yeah, and this type of calculation can rule all them out. Yeah.
Matthias?
Yeah, thanks. Yeah, I was just wondering, so you made this calculation in 1D, and then you were able to compute this suppression even at very high temperature. If you had to plug in some numbers for the 4D, I know you didn't do it, but like some guesstimate, what would this imply in terms of the constraints that you could put on primordial black holes? If you just close your eyes and do something?
Yeah, that would be a bit premature to plug in numbers, but maybe one thing to partially answer here is that, yeah, 2D, okay, like 4D would correspond to this quantity here being of order 1. So perhaps, yeah, but order 1, yes. So I think in 4 dimensions I would expect suppression, kind of reduction of this B naught, maybe by a factor of 2 or a few, but not parametric reduction, I think. But again, I think this number, the precise number, matters because yeah, we have something like in empty space, we have this B naught to be of order 100, and our universe may contain of order 10 to 40 primordial black holes, that some models tell us. So then I basically have to compare B naught divided by this coefficient, you know, which black hole catalyzes. I have to compare with 40, and that may be kind of they may become, you know, comparable. So in this sense, yeah, in this sense, I kind of I really need to find the number. You know, this is a question about the precise number, which is hard to devise from or deduce from this two-dimensional example.
But your rough guess is that it's not a parametric suppression, but some order 1 number.
I think, yeah, my rough guess, it will be order 1 number. Yes.
Thank you.
And if you consider, let's say, rotating black holes, will it help or make things worse?
That's a good question. Yeah, I mean, the most honest answer, I don't know. I would expect like spherical symmetric bubble to be dominating, and it's it seems to be should be more catalyzed by spherically symmetric black hole. But yeah, but it's hard to say a priori. Well, it's also true that the primordial black holes, like production mechanisms that are known, they generically give non-rotating or slowly rotating black holes. In this sense, they are different from astrophysical ones.
More questions?
Following up on Misha's question, like about charge, I guess the production mechanism also predict like the charge should be small, or?
Well, yeah, which charge? If it's electric charge, that would be neutralized by the plasma.
Right, like I'd I mean, seen this in context of magnetic charges, and like relics like these could exist today. So I was asking, trying to think about in that context.
Okay, so yeah, I believe there are some production mechanisms that would give charges under like either magnetic or under other like abelian groups. But again, if you don't put anything in addition, like most kind of straightforward production mechanisms from large primordial fluctuations, that would not give charges. Yeah, that would just be a collapse of large density fluctuations.
Okay,
right.
Thanks.
So yeah. So the answer, I think, is that the charge can or may not be there. Yeah.
You're saying that most naturally all these inflationary models that would produce like really, you know, plain basic Schwarzschild black holes. This is the generic expectation.
Yeah, that's my impression. Yeah, from looking at those models. Yeah, there are different ways to produce these large density fluctuations. Yeah, maybe some of them would naturally lead to some charges. Yeah, besides just, you know, besides just flattening inflationary potentials, yeah, there are other mechanisms which actually may be more interesting even, like production of large inhomogeneities from actually from another tunneling from another false vacuum or things like this. Yeah, maybe some of them can give charges, but I don't think this is a super generic feature. Yeah.
Yeah, I had another question. So your plot here shows this very big difference between the two vacuum, and you were explaining this qualitatively in the talk. But so I was wondering, but then you told me that you are going to fight some sort of small big suppression by the fact that there are many black holes and stuff like this. Is it possible that somehow maybe if some of these black holes are in binaries, and then as a result there's the radiation from one onto the other, and this would bring you more closely to some other like Hartle-Hawking type result, or it's just it doesn't make any sense?
I think it will give additional catalysis, yeah, because now I can have like two black holes together. They produce radiation which can collide, and this possibility of like collision is important actually in this calculation. Still, I think there will be some exponential suppression because, well, because if the separation between black holes is larger, you know, than significantly large, parametrically larger than their radius, there is still the dilution effect.
Right.
Yeah, if somehow like many black holes manage to be together, you know, like very close to each other, yeah, in principle, this type of integration can lead to bigger catalysis. Right, but that, yeah, this I don't know whether it's possible to imagine such a situation when there are many black holes together. No, one thing which may be realized that, yeah, if black hole had the same temperature as the plasma, yeah, for example, if standard model vacuum is more unstable than just from the standard model, if there are some other degrees of freedom which make it more unstable, so they lower the instability scale, and we have a black hole in a thermal bath at some point with comparable temperatures and kind of comparable to the instability scale, then I would expect this strong enhancement, almost like in Hartle-Hawking state.
Mm-hmm. Now this all is happening at super high temperature. So your extrapolation that the standard model doesn't have anything else going on is a very big extrapolation. So this probably means that if you have some constraints, you can always go around them by saying, okay, whatever, there's this other extra thing that changes the potential in the standard model, and I don't have to worry about it. Is that true?
Yeah, I think it's true to some extent, yes, but yeah, you'll have to work harder to argue that, yeah, there is something else and which stabilizes the vacuum. Yeah. Yeah, I think it's good to know. I think it's good. Yeah, I think it's good to know how to do this type of calculation. Maybe eventually, you know, after some more studies, we will be able to make more reliable estimates, more precise estimates, because yeah, repeating every time this full calculation may be hard and not sensical. But yeah, perhaps we will have some good reliable estimates. Yeah, and then for a given model, these estimates can be applied, and it can be seen right away whether there is this threat of black holes to the vacuum or not. Yeah. And also, yeah, and also there's like extension beyond standard model. In principle, they can act both ways. They can make our vacuum more stable, but they can also make it more unstable. Yeah, so in principle, it depends.
Yeah, if you use some, you know, popular extensions of the standard model, like something like SUSY, then will the picture change? What will happen there?
Yeah, what SUSY does? Yeah, there the Higgs sector is more complicated anyway. So
I guess it will depend on the details of the completion.
Yeah, I think it may depend very much on all the coupling, because you know, like already this picture depends very sensitively on the top coupling, which is measured with some you know, like some uncertainty. And actually within 2 sigma, I think the standard model vacuum can be totally stable. Yeah. So one thing which would definitely destabilize the vacuum is more heavy fermions coupled to Higgs, like vector-like fermions or something that couple to Higgs. And yeah, we didn't see them because they are too heavy, but they would destabilize the potential further. On the other hand, if I have some heavy like a scalar that coupled to Higgs, they can turn it around the other way. Or yeah, so Yeah, I think it's quite model dependent. Yeah. Like in SUSY, I believe it will depend on the parameters.
More questions? So if not, let's thank Sergey again.